Today we're going to talk about parasitic drag. As we introduced in class, parasitic drag is the combination of both skin friction drag and pressure drag. Remember, skin friction drag is that drag from the shear stresses, whereas pressure drag is from the pressure. Okay, in class we also talked a bit about laminar versus turbulent boundary layers. Just to kind of review, let's see. This is what these profiles look like. So a laminar boundary layer, shown here in blue here, it has, it more quickly recovers towards higher speeds, whereas a turbulent boundary layer has higher velocities close to the wall. You can also look at it in terms of height. A laminar boundary layer is not as high or as tall as a turbulent boundary layer. So more than that, the important things to understand is kind of the physical differences between a laminar and turbulent boundary layer. So laminar, meaning layers, you could think of it, and it's meant to, it's called that way because it's kind of descriptive of how the flow is. It's almost like little sheets of fluid particles. So let's say, here's the wall. I've got some slow moving particles, and then maybe another layer on top of that faster moving, and another layer on top of that even faster moving. So I've got kind of this boundary layer, and there is momentum exchange, but it's not very much, right? There's not as much momentum exchange. It kind of behaves like these separate layers. Whereas in a turbulent boundary layer, you still have all these particles, but they're moving in a bunch of different directions. On average, yeah, they're still moving forward mostly, but because they're interacting and swirling around, there's a lot of exchange of momentum and energy. Because of that, that's why this height is much bigger, right? There's exchanging energy, so it's pushing out further out into the flow field. That's also why you see this larger profile closer to the wall. Because of all that energy exchange, there's more momentum in the fluid, and so close to the wall, you can see higher velocities. So this has some real implications for drag, as we briefly introduced in class. In an introductory fluids class, you often hear this golf ball example. And just to recap, the idea there is that with a golf ball, rather than having a smooth ball, which will have more laminar flow, added these dimples, right, to increase turbulence. One for drag. And the reason is that, as we talked about in the previous class, that fluid is going to come around and it's going to separate and create this wake. And a turbulent boundary layer, as we're seeing here, actually carries more momentum because of all that energy exchange, more momentum close to the wall. So it can actually traverse further along the cylinder before it separates, which means that my wake is smaller and I have less pressure drag. However, it has more skin friction drag. So if I'm looking at just this flat plate version here, the turbulent boundary layer is also, even though it's interacting with other fluid particles, it's interacting more with the wall. So it's rubbing more on the wall, if you will, creating a lot more drag. So in general, a turbulent boundary layer will have more skin friction drag, but potentially less pressure drag. It's not always so cut and dry, but that's kind of the trade-off here. So for an airfoil shape, which is not quite a cylinder, ideally, if I'm at low angles of attack, I want lots of laminar flow. That has low skin friction drag, nice and smooth. That's why you'll see with a sailplane or a performance yacht or something, right? Really smooth, polished surfaces. So I can have nice laminar flow and low drag. However, as I get up to higher angles of attack, then this starts acting more like a blunt body, right? And as the fluid comes around, it's likely to separate, right, at some higher angle of attack. Whereas if I have some turbulence, I may be able to delay that separation a bit later and keep my airfoil attached to higher angles of attack. So there's a balance, there's a trade-off here. I want laminar flow, maybe especially early on in my airfoil, but I do want it to be turbulent at some point so I can navigate this adverse pressure gradient. So same idea here with the cylinder, right? Remember, we went from high pressure to low and then back to high. So on this backside, as I go from low to high, I'm doing work. I'm moving against this pressure. We call it an adverse pressure gradient. So I need that momentum. The same thing happens on an airfoil. Low pressure, or sorry, high pressure at the stagnation, but it happens much quicker. I've got a low pressure peak here, and then I have this long recovery as we talked about last time as I move back towards higher pressure. So I generally want laminar flow towards the front, and then at some point get towards turbulence so I can be delay stall up to higher angles of attack. There's another way to view how this happens along an airfoil. In general, an airfoil is not laminar or turbulent, right? It's going to have all of the above. Start with the stagnation. As the Reynolds number, start with laminar flow, and as the Reynolds number increases, as we move along the airfoil, it will become turbulent because of the instabilities, and then at some point it may separate, hopefully closer to the trailing edge, and then I have some wake. So you can see depicted here both skin friction drag and pressure drag, right? The skin friction drag is the drag due to the fluid moving across the body from shear stress. The pressure drag is really the difference between my velocity profile upstream and downstream. Because of that wake, I have a velocity deficit. So I've got this high pressure here, low pressure here, I've got a drag. In an ideal world, if I had no pressure drag, the flow would move past the airfoil and would come back perfectly straight, right? Nothing happened in terms of the velocity field. That would have no drag, but because of the pressure losses, I'm going to have this deficit in the wake, and that's going to be manifest as a pressure drag. Both of these are going to show up. So this background helps us to start on how we might analyze a wing. In class, we kind of looked at an airplane like this, and we were trying to estimate the drag on the wing. We're gonna talk about wings and fuselages, but this is really representative. Could be a wing, could be a tail, anything like this that's a lifting surface. These are thin. Yeah, almost like a flat plate. So that's actually what we're going to start with. We're going to look at a flat plate. Flat plates are well studied. There's a lot of experimental data, and in fact, there are analytical solutions for some things. So let's look at a flat plate. Here's my flat plate here, and it's got a boundary layer developing. Of course, I would have it on both sides. On the left, this is what's called a skin friction coefficient. Okay, so CF is my skin friction coefficient. Essentially, it's a drag coefficient for this flat plate here. And this formula that we're showing on the left is actually an analytic solution based on the boundary layer equations. And what it says is that my skin friction coefficient is a function of my Reynolds number, which means that it changes. So Reynolds number, just to remind you, rho v x over mu, where x is my distance as I move along. So as I move along, my flat plate, my Reynolds number is increasing. If you were to plot the skin friction coefficient, you would see that it actually is really high, right? Because the Reynolds number is going to be really small at the leading edge, and so this is in the denominator. You're going to have this big peak, right? And it's going to kind of taper off, maybe not quite as aggressively there. It's going to have kind of the square root 1 over square root of x behavior. So what does that mean? From a design perspective, that means a lot of my skin friction coefficient happens right towards the leading edge here at the beginning. Okay, so from a skin friction drag point of view, most of it occurs right near the beginning, and then it sort of tapers off, becomes less and less as I go further. It's still contributing, but most of it is right up towards the front. So if you're designing your airplane, you'll see a lot of these model airplanes will have tape right towards the front, but not put tape towards the back of the wing. And the reason for it is that I get the best bang for my buck by putting it towards the front. As I put it towards the back, it may help decrease drag a bit, but it adds weight and it may not be as useful a trade-off. Whereas towards the front, that weight penalty is worth decreasing some of that drag. So you often see that, right? Smoothing out the leading edge. And ideally, sometimes, we'll use layup or a laminate or something to get smooth surface everywhere. But if we can't, and it's going to be tape, which is going to be heavier, we'll generally just put it towards the leading edge. For turbulent flow, there's no analytic solution. This is just a fit to empirical data. There are many fits. Here's just one example. That shows how this would vary for a turbulent boundary layer. As we talked about, an airfoil is not going to be fully laminar or fully turbulent, but for you to do your estimations, I would generally recommend that you just assume it's fully turbulent. That'll be actually pretty close because, for one, your model aircraft are not going to be super smooth as, say, aerospace grade materials. You're going to have some rough edges. You're going to have propellers and a bunch of you'll have some control surface, various things on your airfoil that are going to make it rough. So it's actually not a bad approximation to assume it's fully turbulent, especially because we're flying close to the ground in the planetary boundary layer where there's a lot of mixing. So I would do that, one, because it's pretty reasonable, but also because it'll be a bit conservative, which is probably best, right? To overestimate the drag a little bit. If you want to get fancier and to consider an airfoil that's partially laminar and partially turbulent, I do discuss this in the text. It's a little more complex, but totally doable if you'd like to go that route. Okay, so this is really the first step, is that we figure out the Reynolds number for our aircraft. And then we can plug in these formulas and figure out what the drag coefficient or skin friction coefficient would be for a flat plate. Now, an airfoil, or a wing rather, is not a flat plate. It's pretty thin, but it's not a flat plate, so we need to make some sort of correction. This is going to be called the form factor, and it accounts for the fact that my airfoil is going to be not flat. And as you'd expect, the biggest parameter that affects, an airfoil not being flat is the thickness. So here it is. It's called the form factor. K is the form factor. And as you can see, it's primarily a function of this thickness ratio. So as you can see in the plots, as my thickness ratio goes up, my form factor increases. If my thickness was 0, my form factor is 1. And so this is a number that we're going to multiply against our skin friction coefficient. So for, again, a thickness of 0, flat plate, the multiplier is 1. I get back my flat plate solution as I would expect. But as my thickness increases, so if I've got a 15% thick airfoil, right, I multiply my skin friction or drag coefficient by 1.35 or whatever it is. Okay. You'll notice that there's also some effect of sweep. That's what lambda is, right? It's my sweep. So as I sweep back, it decreases my form factor a bit. This is going to be a small effect for us, especially because we're going to be at very low to 0 sweep generally. Okay, so again, just to recap, the idea here is that we're going to use solutions that we know from flat plate theory, and then we're going to correct them. We're going to add some thickness for airfoil just based on empirical data, and this is going to help us get a better estimate for drag coefficient for a, I'm calling it a lifting surface. It could be a wing, tail, these kind of things that are relatively thin. I want to emphasize here, this is, of course, very crude. What we're doing is what we call conceptual design. We'll talk about methods later, and if you took the aerodynamics class, we get into how you actually compute this in more detail for a wing. But in general, this is complicated. If I got a wing, I need to know the detailed shape. I need to know all my flow conditions, and that's going to help me estimate how the drag varies across the wing, and I can integrate across the wing or use various methods to estimate the drag. But I'm at a conceptual stage where I don't necessarily even know what type of airfoil I'm going to use and the exact conditions I'm going to fly at. Really, I want to be able to just be at the conceptual stage where I'm trying to size this. What type of span should I have? What should the aspect ratio be? Approximately how thick do I want my wing to be? I need to work at sort of this high level so I can explore the design space. This is kind of the realm we're starting in right here. Again, we'll look at more sophisticated methods later, but this is kind of this first rough cut conceptual design, if you will. Okay, so we're going to put these things together. My drag is going to be given by my skin friction coefficient, as we said, and we're going to multiply by this form factor. And remember, drag coefficient is drag divided by dynamic pressure and area. So if I want to get drag, I need to multiply multiply those back. So I need to multiply by my dynamic pressure, and I need to multiply by an area. So what area is relevant if I'm looking at a sort of drag across my wing? Well, it's what we call the wetted area. Okay, so I need to describe what that is. Wetted area is like if I took my airplane and dipped it in a fluid, or it is in air, but maybe it's easier to see if we dipped in oil. What is the part that gets colored, right, or covered by the oil? That's the wetted area. Those are the surfaces that the fluid is moving over and are causing the skin friction drag. So again, this is entirely skin friction. This is a correction that adds a pressure component to it. We're assuming, again, these thin geometries, aerodynamic geometries that don't have a lot of pressure drag. So there's a small correction that adds for this, that accounts for that increase. We also are going to want to non-dimensionalize this. Our drag coefficient, remember the definition, this is just from last time. It's the dynamic pressure divided by the reference area. So if I plug that in, I would get K times CF, and the dynamic pressures would cancel out, and I get S wet over S ref. Okay, so this is a formula for our drag coefficient. Again, notice a few things that if K was 1, if it was a flat plate, and all my areas were equal, right, if those, I got rid of those, then this skin friction coefficient is a drag coefficient, basically, right? Just we've corrected it for thickness, and now we have to figure out the differences between these areas when these would not necessarily be the same. And in general, they're not. In fact, actually, they're really always not. So what is the difference between these? Well, maybe it's best to illustrate it. Let's look at the same example we showed last time when I defined the reference area. So here's, let's say, the cross-section of my fuselage, and I've got a wing. This will be easiest to do with a commercial aircraft here. Say it extends through the wing here. Actually, let's see, how should I draw this? I'm going to draw a wing with leading edge, trailing edge extensions, kind of like this. Okay, so here's my wing, comes through, and in general, it's going to extend into the fuselage as well, right? This is the carry through into the fuselage. And maybe carry straight, but I'm just going to draw it that way. Actually, let's just draw it straight. It's going to carry straight through the fuselage here, and then something like that. Pretend I drew it symmetrically there. Okay, so that's my wing coming through the fuselage. Last time we said the wetted area, the reference area was this trapezoid. So I just took a trapezoid and I drew it like this and like this, right? And I drew that really poorly. So let me make this more symmetric here. Oops. Okay, so here's my trapezoid. This is my reference area. Again, a reference area is just a reference. It's just something we use in normalizing the drag coefficient. It's somewhat arbitrary, but by convention, we use this trapezoid. It's just something that scales with my airplane. As I make my airplane bigger or smaller, this is a natural sort of scaling parameter. Now the wetted area, so this is reference area, the wetted area is the area of the wing that's actually going to get wet, if you will. And that is all of this area here, right? Around here, okay, all of this area, and then the same on this side. Okay, the part inside the fuselage doesn't get wet because it's covered by the fuselage, but also it's really top and bottom. I say top and bottom, but it's of course all sides. There's a front, back, it's a three-dimensional shape. It's not this projected area. The trapezoid is really just this 2D projected area. It doesn't have a top and bottom. But this wetted area, this is this entire surface again, right? We dip this in ink and we're trying to see what parts are colored by that ink. And here it's so approximately it would be this flat shape times 2, right? Because I've got the top and bottom surface that the fluid is moving around. In the book, there's also a correction for thickness, right? Because this is thick and has this three-dimensional shape. And at this stage, we don't actually know the exact shape. We can approximately get it from thickness. In fact, I've got that on this next slide here, right? So this is what this is saying. If I took this exposed area, which is this, of course, flipped on the other side too. I should probably draw that just to be clear. The exposed would also be this part, right? It's just everything that's exposed to the fluid. To get my wetted area approximately, I multiply by 2 because there's a top and bottom. And then there's this correction for thickness. So as I make it thicker, that adds a little bit to my area. And so this is just again, a rough way to kind of estimate what that wetted area is going to look like. Okay, so this is how we do this for lifting surfaces. Again, so like wings, horizontal, vertical tails, winglets, these kind of things, you can use this kind of method. We're going to do the same method for fuselage. You can think of this as anything that's like a body of revolution, something that's like cylinder-like. A fuselage, it could be nacelles, pods, engine pods, things like that. We're going to use the exact same method. It's a bit more of a stretch because these are not quite as thin, but we'll use the same idea. In other words, we'll take the flat plate skin friction thing, that hasn't changed. The only thing that's going to change is that we're going to use a different form factor. So instead of a form factor that's kind of based on these airfoil shapes, we use a form factor based on these cylindrical shapes or bodies of revolution. So here's what it looks like. I've got this body of revolution. It's got a length and a diameter. So I'm going to define this parameter called the fineness ratio. It's just a ratio of that length to diameter. And then I can plug it into this formula to get my form factor. And so what you can see is that as the form factor gets really large, right, it's very long compared to the diameter, then this approaches 1, which just means, as you'd expect, as this becomes really lengthy, it basically acts like a flat plate again. But as the fineness ratio gets smaller and smaller, this becomes more like a blunt body, and I need to add a bigger and bigger multiplier in my drag to account for the fact that these flat plate values I'm using are no longer appropriate. If you get much smaller, right, as we're getting to 5, 4, 4 or so, then this fit is probably not appropriate at all. You're going to get a lot more drag. But this is just, again, conceptual design, early stage, to get kind of an estimate of our aircraft drag. We'll do more detailed methods later. Same procedure. You need a way to estimate the wetted area. Here's an example. For the cylinder part, that's really simple. It's just going to be, a length times that circumference. Whereas for these cones, if you wanted to estimate them, here's just sort of a rough estimate of what that would look like. Okay, so the last thing we're going to talk about is drag coefficients, adding these together. So what you're going to do, let's say I've got wing, and I calculated the drag coefficient for my wing, and I've got a tail, and I calculated the drag coefficient for my tail, and I've got, say, this fuselage, and I calculate the drag coefficient for my fuselage. The question is, can I just add these together? Is my aircraft drag wing plus tail plus fuselage? And the answer to that is maybe. Okay, it depends how you use your reference areas. So we can always add the drag. We can say our total drag is the drag of the wing plus the drag of the tail plus the drag of the fuselage. These are just forces, right? And we can add forces together. Okay, so let's see what that means if I can add coefficients. If I use the same reference area, right, then these are all just, this is the definition of a drag coefficient of the wing, tail, fuselage. If I use the same reference area, then yes, I can add them together. If I had used different reference areas, right, if I had used D wing over Q over S of the wing, but over here I use the tail, then I can't just add these together. So generally what one does is we use the same reference area for all the components, and we still just use that trapezoidal area for the wing. If you did the separate ones, right, then you'd have to multiply this by S tail over S wing, for example, so we could get them on a common denominator. Then we could add them. But just as a matter of practice, we generally use the same reference area for all of them. And that way we can just add drag coefficients just like this without worrying about it because we use the same reference area. All right, so to recap again, what we're doing here is a very simple method, again, conceptual design. We'll get into some more detailed methods. We'll use some programs to help us estimate drag a little better. But at this stage, we just want a rough cut. We want to know approximately what size we should be at, you know, what kind of speeds we want to fly, what kind of wingspans we want to get to. And these kind of methods work pretty well to get us there. Again, it's based on this idea of flat plates. We know skin friction drag for those really well. We're just going to add this correction for thickness to account for, say, a thickness of the airfoil or the slenderness of a fuselage, and then account for how much area is actually being affected by the fluid. So that's really the basics of how this works. If you look in the text, there's some other little more advanced details on making corrections for Mach number and sweep and you know, accounting for some thickness in the wetted area. But at a basic level, a lot of these will be very small changes, but these are things that you can look at in the text if you want more detail. So next time we're going to talk about some other components of drag. This is again parasitic drag, which combines the skin friction and pressure drag. There'll be a few other components of drag that are important for aircraft that we'll talk about in the coming